Hey everyone, and welcome to this explainer. Today we're stepping straight into the laboratory of clean. We're going to uncover the invisible, molecular magic behind something you rely on absolutely every single day, probably without even giving it a second thought. Soap. You know, what happens when you lather up your hands isn't just basic hygiene. It's actually a super dynamic, elegant chemical experiment happening right there at your bathroom sink. And it's all driven by a fascinating process known as saponification. Okay, let's quickly run through our game plan for today. First up, Section 1, the meaning of saponification. Then, Section 2, the three-step mechanism. We'll follow that with Section 3, acid versus alkaline hydrolysis. After that, Section 4, transforming fats and oils. And finally, we'll wrap up with Section 5, the anatomy of soap.
All right, let's dive right into Section 1, the meaning of saponification. So let's start by unpacking the topic itself. Saponification. It's a pretty intimidating multi-syllable chemical term, right? But what does it actually mean when we strip away the lab codes? At its core, saponification is just the alkaline hydrolysis of an ester to produce a carboxylate salt, which, spoiler alert, is the chemical identity of soap, alongside an alcohol byproduct. Now, chemists absolutely love their highly specific, complex terminology, but the history here is actually beautifully simple. If you look at the root of the word, it's derived directly from the Latin word sapo. And sapo quite literally just translates to soap. So despite how complex it sounds, saponification just means soap making.
Think of this as our basic recipe. You start with an ester and react it with an aqueous base, which is typically sodium hydroxide. And the result? You get your sodium carboxylate, again, that's our soap, and an alcohol. To give you a really specific laboratory example, if you take ethyl ethanoate and react it with sodium hydroxide, you're going to produce sodium ethanoate and ethanol. It's a remarkably clean, incredibly predictable exchange of chemical bonds that gives us the exact cleansing product we're looking for.
Moving right along to Section 2, the three-step mechanism. Now that we know the overarching reaction, we're going to zoom way into the microscopic level. We want to witness exactly how this reaction unfolds in real time, bond by bond. This molecular drama plays out in three very distinct acts. Step 1 is the nucleophilic attack. Think of this almost like a chemical ambush. The hydroxide ion aggressively targets a vulnerable, partially positive carbon atom, and that forms a temporary, highly unstable structure. Then, in Step 2, elimination, that unstable structure basically collapses in on itself and forcefully kicks out an alkoxide ion. And finally, Step 3 comes in to finish the job.
Now, what's really fascinating here is that Step 3 is the absolute climax of the entire process. The carboxylic acid that was formed just a millisecond ago immediately reacts with any leftover hydroxide ions to produce the final carboxylate ion and water. And this specific step, it's the point of no return. It makes the entire reaction completely irreversible. It locks those products into place and guarantees that the reaction goes all the way to completion.
Let's pivot a bit to Section 3, acid versus alkaline hydrolysis.
Let's set up a bit of a chemical head-to-head showdown. You see, in organic chemistry, you usually have more than one way to break a molecule apart, so we need to compare the acid pathway against the alkaline pathway. Looking at the lab data side by side, the contrast is actually pretty stark. Acid hydrolysis relies on dilute acids like hydrochloric or sulfuric acid, and it yields a carboxylic acid and an alcohol. Alkaline hydrolysis, which is our saponification process, uses strong bases like sodium hydroxide or potassium hydroxide, yielding a carboxylate salt and an alcohol. But look closely at the underlying mechanics here. Acid hydrolysis is a reversible reaction, while alkaline hydrolysis, as we literally just learned from Step 3 of our mechanism, is completely irreversible.
So, what's the bottom line? Because acid hydrolysis is a reversible process, the reaction is basically constantly fighting itself, pushing forward and then pulling backward. Naturally, that results in a lower overall yield. Alkaline hydrolysis, on the other hand, is a strictly irreversible one-way street, which results in a significantly higher yield. And this is exactly why alkaline hydrolysis is the undisputed champion for industrial soap making. When you're manufacturing soap on a massive scale, you absolutely need a reaction that pushes firmly and permanently in one direction to maximize your product.
All right, let's jump into Section 4, transforming fats and oils.
Time to zoom back out to the macro level. We've seen all the abstract molecular mechanisms, but now let's explore how these exact microscopic rules apply to the physical fats and oils we actually encounter in everyday life.
The raw materials for this industrial process, the literal fats and oils you'd find in nature or even in your kitchen, are scientifically classified as triglycerides. To a chemist, a triglyceride is specifically a triester of glycerol. This big, bulky, naturally occurring fat is the primary starting material that we feed directly into the saponification process.
And this brilliantly illustrates the incredible mathematical and chemical efficiency of this reaction. Because a triglyceride is a triester, meaning it literally has exactly 3 ester bonds built right into its structure, it requires exactly 3 molecules of our base, the sodium hydroxide, to break it down. And in return, it produces exactly 3 molecules of soap. It's a perfectly balanced, highly efficient 3-for-3 chemical exchange.
Let's put that perfect exchange into a real-world chemical equation. We take our fat, which is represented here by this huge molecular formula for a triglyceride, and we add our 3 molecules of sodium hydroxide. Boom. The reaction yields 1 molecule of glycerol and 3 molecules of sodium stearate. I really want to anchor this to reality for a second. That sodium stearate product resulting from this reaction, that is literally the solid bar of soap sitting in your shower right now. That is the tangible, real-world result of this entire chemical journey.
And finally, we arrive at Section 5, the anatomy of soap. For our last section, we really need to look at the tool we just built. Let's deconstruct exactly what makes this newly synthesized molecule so remarkably effective at doing its job, which is keeping us clean. The true secret to soap is its fascinating, almost two-faced nature. A single soap molecule, like our sodium stearate, is split into 2 very distinct parts with entirely opposite personalities. On one end, you've got a long, nonpolar hydrocarbon tail. This tail is hydrophobic, meaning it actively fears and repels water. But on the exact opposite end, you've got a polar ionic head, and this head is hydrophilic, meaning it absolutely loves water and actively seeks to bond with it.
Which leads us to this final million-dollar question. How does a single molecule with a water-loving side and a water-fearing side actually manage to lift invisible dirt off our hands every single day? It's a complete structural paradox. Well, when you wash your hands, that water-fearing hydrophobic tail burrows into and grabs onto the grease and oils on your skin just to get away from the water. Meanwhile, the water-loving hydrophilic head reaches out and grabs onto the running water from your faucet. The water pulls the head, the tail pulls the grease, and the dirt is literally ripped away from your skin and washed safely down the drain. Honestly, it leaves you marveling at the incredibly complex, beautifully structured chemistry happening right there on the surface of your skin every time you wash up. Thanks for joining me for this explainer. Keep wondering and keep learning.